Hello, so let's make sure this is working. Awesome. So the goal of this video is to implement the equation that we derived in the last video and to show how what we are going to do works, but once we bring in a certain or a higher number of time increment, the environment doesn't enjoy it. But what we need to do initially is import our old friend numpy as np, sorry, and then we need to say from plotly dot subplots, or plotly, sorry, dot subplots import plot, or make subplots, and that should be it. Okay, cool. And so now what we need to do is we just need to define some of our constants and our variables, and the first one that we need to define is our thermal diffusivity alpha. Alpha, there we go, which is equal to 1, and then we have the number of increments in our bar. We want that to be equal to 50, and then we could say let's measure the temperature at 2,000 time increments as we go along in our bar. And so the next step is to define the size of each increment, both time and the size of our bar. And so we could say, all right, let's say our, let's just do delta x. We can say that is equal to 1. Nope. And then the size of our time increment, we can say, all right, let's make that 0.1. And then in the last video, I wrote out that in the equation we derived, we had just outside the parentheses for measuring the time or the temperature between positions in the bar, we had that the thermal diffusivity times our time increment divided by our bar position increment squared. What we're going to say is we're just going to pick a different variable and include all of that, so that way we don't have to write that out each time. So we're going to say R is equal to alpha times our time increment divided by our bar size increment squared. And so now we need to specify the initial temperature of the bar across the bar in this situation. And temperature, again, is arbitrary because we're going to just graph it as we go along. But what we're going to say is the temperature across the bar for our entire array is equal to the number of increments that we need, because we have to specify the shape. And we're going to say that the temperature we want is, let's do 25 degrees Celsius. And so we can do that. And so if I said, okay, give me temperature all the way across the bar, we get 25 degrees Celsius. And so then if we wanted to say, all right, our first node or our first increment in the bar is equal to 50 degrees Celsius. Oh, we want that as a decimal, sorry. And then the last increment, and so I could say, all right, it's because it goes from 0 to 49. I could say, okay, T49, or I could say T-1 is equal to, let's say, 80 degrees Celsius. And if I say, okay, show me temperature now, we get 50, 25, 25, 25, all the way to 80 degrees Celsius, which is what we want. And so the next step is, now that we've defined our constants and variables, is we need to introduce that formula we derived into this. But what we're going to do is we're going to set up our environment so we could plot our, oh my gosh, I have a frog in my throat. Plot our equation, and we can see the temperature of each node in the bar as time increases. But we're going to say that our figure is make subplots with rows equal to 1 and columns equal to 1. And then we're going to say, okay, let's add a scatter plot. And the first step, since we can't even plug anything in here because we don't have any x variables defined. And so, can you go away? Thank you. And so what we could say is, okay, our x value is, wow, a numpy a range from the number of increments that we have in the bar, which is 50, times the size of our increments. So we said, okay, we have 50 increments times 1, 50. So we're going to go from 0 to 50 all the way across the bottom of our graph. So now that we have that set up, we could say, all right, our x variable is equal to x, y variable or y-axis is equal to t. Sorry. And then we could say that the name of our graph is equal to, let's do initial conditions. And so we get that. And so from node 0, we have 50 degrees Celsius. Then immediately in node 1, we have 25, all the way to node 49, which is 80 degrees Celsius. But again, from 0 to 49 is 50 total. So if we wanted it to be clean, we could say, okay, let's do, where'd it go? We could say, okay, we have 51 increments. Now we have 50th node is equal to 80, 0 is equal to 50, but we're going to keep it at 50. Awesome. And so the next step, what we're going to do is we're going to now implement our equation. And so what we're going to say is for I in the range from 1, our first node, to our number of time increments plus 1, we want the temperature of all of our previous nodes. So we have 1 to our last node. We want that to be equal to the temperature of our second node all the way to our last node, plus that R value times the temperature of the previous, our second position node, minus 2 times the temperature of the middle nodes at the previous time. So we're going to say 1 to -1. Nope, sorry. I already put the 2 in. And then we're going to add the temperature of the nodes shifted 1 to the right. And so we're going to say, all right, let's go from the beginning all the way to, so -1 would be the 49th node, so we're going to go to the 48th node. We're going to do that, make sure that so now if we take this and put it here, I don't like the red. Array is one-dimensional, but 2 were indexed. Oh. Awesome. And so now we could say, let's do, and so we have the temperature of just the one all the way across, or this initial one that we plotted. And so to incorporate the other temperatures, we can say that if the value for I modulo 100 is equal to 0, we only want to see temperatures that are plotted, or time increments at a whole number, instead of seeing all of them with each single time increment, because we don't want to see, what is it, a gajillion time or time plots. And so we can say, okay, we can add a scatter plot using, again, x is equal to our x variable, y is equal to our t variable, and then we want it as with our mode to be equal to our lines, so we can see the curve of each node or increment in the bar. And then we can say that the name of our graph is equal to awesome. And so if I'd said, okay, let me see the graph. So what we have is the temperature for each one of our increments in the bar, going from the first one all the way to the last one, and how they increase with time. And so let's say, okay, we're going to increase our time increment from 0.1 to 0.3. I don't know how obvious of a change will be. Okay, so we can see, all right, since our time increment changes, obviously it's not going to be as close together. And so what if I said, okay, let's change it to 0.5 and our half a second for our time increments? They get further and further apart because, again, we're seeing less and less time values. And so I said, all right, let's try and ramp it up a little bit. Let's go to 0.7 seconds for each time increment. And so once it iterates down here, our graph's super messed up, which is bad because obviously if we had a bar this hot, that's hotter than anything I think ever discovered in the entire world. So, okay, we know that that doesn't work. What if we bump it back down to 0.6? Nope, that's... So our y-axis went down, so we know it's getting less hot. But again, this is impossible. So I said, okay, let's go to 0. We knew it worked at 0.5. Let's try 0.55. So again, the y-axis goes down, but we need to incorporate. Let's try 0.505. Okay, so now we're at less, or it's becoming less and less hot. And so, okay, what if I did 5001? So we know the reason that this happens is because our R value, we haven't set it up in a way that gives a stable condition, and the way that we've derived it at this point gives an unstable condition. And the goal of the next two videos, and then the two is I'm going to derive it out in OneNote again, and then we're going to implement it the correct way, and we won't be getting squiggly line graphs.